yeah, like probably only on Monday, but my plan was to show like some results from papers because in the end, like for the so the plan was to talk about gravitational waves on Friday and then to show some results on Monday, like from the papers, because it doesn't make much sense if I draw the plots on the blackboard. So I thought I would just show exactly. So I was going to do that anyway. Okay, so I hope I didn't scare. I scared some people last time, it seems.
No, they're coming.
Actually, that was already a hard part, so no, from now on.
What?
Last time was kind of a hard part, from now on it's going to be.
Now it's downhill?
Now it's downhill, exactly, but in a good way. Okay, let me already start writing.
Okay, just want to say this is the 6th lecture of Benedict. So it's 2 more lectures on Friday, and on Monday is the last one. And I have to say that we have a change in schedule Monday. So it's going to be at 1 p.m.
Okay, fine. Yeah.
Okay? On Mondays at 1 p.m. because there are some lectures going on here. Yeah, so is the mic on? Everything is on? So I think, right. So I think, yes, please.
Okay, so yeah, let's start. So last time, so we discussed this problem of tunneling in quantum mechanics. So we have some state localized in a potential and some position x0, and we want to know what's kind of a tunneling or decay rate from this vacuum into a deeper true vacuum. And yeah, then I derived this formula for the decay rate. Okay, so I derived this formula where kind of this part is very difficult to calculate, but it's like this functional determinant. But it's much less important than this exponential here, because it's an exponential. And this guy here is easy to calculate. And the way we can calculate it is, so it maps to the problem of a classical particle moving in the inverted potential. And starting off at x0 at t minus infinity, then doing something, and then ending up again at x0 at t infinity. So, and yeah, so how we got there was to kind of we got a like path integral expression for the energy of the state, and then we expanded this path integral expression around the minima of the Euclidean action. And the rationale was that the minimum of the Euclidean action, that those give the dominant contribution to the path integral, and then from there we could extract the energy, and then the decay rate is given by the imaginary part of the energy. And then we discussed two different. So we were looking now for stationary solutions to the Euclidean action, we discussed two possible solutions. One was where the guy just sits here for eternity, but then we saw this just reproduces the ground state energy in this minimum here, so it gives no imaginary part, so it's not interesting. And then the other part we discussed was like, so the field, the particle starts off here, then rolls down, bounces off here, and rolls back. And that's a so-called bounce. And the rationale was, or I mean, the intuition behind this is that kind of this path probes the barrier of the potential, so it's more likely to have something to say about the decay rate, and indeed it had. I mean, then as I discussed, I mean, I couldn't discuss it in much detail, but as I discussed, like if you consider this path, you find that there's a imaginary part of the energy, because you have to do some energy continuation to make sense of this, and then you get a non-zero contribution to the decay rate. Okay, so and then I discussed how to generalize this to quantum field theory. Let me just write down this expression here, because I'm going to keep it for later. So the generalization is straightforward now. There's again like some ugly, complicated functional determinant, which we will never actually calculate, so it doesn't really matter. And now this functionally determined, and the operator contains the spatial derivatives also. So it's literally the same thing. So yeah, the problem we are looking at is now, I mean, the same problem is from field theory. So we have a scalar potential. This is the minimum. This is what I call phi naught, and we want to know kind of if we are in this minimum initially, what's the decay rate into this minimum, right? And so phi naught is what appears here, and this is kind of, this is the bounce path. So, okay, so now we have to discuss how to calculate this exponential b, which is the bounce action. Now in the QFT case, action now is given by the Euclidean action evaluated for this path describing the bounds, and I will tell you in a few minutes what this looks like. And the Euclidean action for the scalar field theory is just given by tau in Euclidean space, d3x, and then we have kinetic term. Maybe I write this best. Okay, let me continue here. Sorry, it's a bit ugly. Time derivative with respect to tau, spatial derivative, and this bound solution is a stationary point of the Euclidean action. So it's a path, a function that axiomatizes the action. Point of Euclidean action, and we know how to determine the stationary points of an action by the order Lagrange equations. Lagrange equations for field theory tell us that the equation of motion that this path has to satisfy is just the usual one for a scalar field. The only difference is that now we're in Euclidean space, so the time derivative is switched. Okay? There's the derivative of the potential with respect to phi. Okay.
With some boundary conditions.
Exactly. So, and the boundary conditions are can you still read this? So one condition is that the limit of this pass so it's a function of tau and x, and if I send tau to plus minus infinity, I should get phi naught. So this is now what corresponds to the boundary condition that we had before for the path, right? So now we have a path that, again, I erased it, but just draw it again here. Potential. What is this? Function, some path, and a path integral which starts here at tau minus infinity and then it's again here at tau infinity. That's exactly the same thing.
So phi naught can be a function of x, right?
Yes, exactly. Yes. But no, phi naught, no, sorry. Phi naught is a constant, right? Phi naught is really like the value of the just the minimum of the potential. So this is the same as before, and now we have another condition that is new in quantum field theory, and that is a condition that if we send x to infinity, again, so now it's absolute value, x to infinity, it should also go to phi naught. And the reason for this boundary condition is that we want the action, we want to study configurations with finite action. So we've normalized our potential in such a way that the zero of the potential is here. So configurations that kind of end back here at spatial infinity, they have a zero Euclidean action. So this is just a condition that the action of my bounce, of my instanton, is finite. Sorry, I don't know if you can read the less action. Finite. Okay, so this is already a lot simpler than studying this complicated tunneling problem. But now we can simplify it even more using the following theorem. Theorem. Which was proven by Coleman and then two other authors, Glaser and Martin in 1978. The theorem states that O4 symmetric solutions to the Euclidean equations of motion, so to these equations of motion, always have lower action than non-SU O4 invariant solutions. Have the lowest action. Again, since we're interested, we are expanding around the prism around the minima of the path of the action, these are real configurations. We can restrict ourselves to because I have done this action. So how do I continue now? Okay, let me. I will erase this again because I need the space here. So we will just restrict ourselves to four symmetric solutions. And this means that now our bounce, which in principle is a function of the four coordinates of Euclidean space, we can restrict it to a function of just one coordinate, which is kind of the radial distance in the space. So rho is tau squared. That's x squared. Right. Okay. And that helps a lot because now this was a four-dimensional partial differential equation. And now using this theorem we can boil it down to just one dependent variable. One independent variable. Okay, so now if we just plug this onwards into this equation of motion, what we get is, and I write it here now, is I want to keep it for later. We check what we get is following. Here, evaluating this derivative, I get a second derivative with respect to rho and a first derivative with respect to rho. And then the boundary conditions here, those combine, so those for tau going to plus minus infinity, those for absolute value of x going to infinity. So they just combine into the following boundary condition: the limit of rho going to infinity of this configuration has to be phi naught. And now there's a second condition that we have to impose, which is this derivative of phi bar with respect to rho evaluated at rho equals 0 is 0. And this is just necessary to ensure that the solution is not singular at x equals 0 and tau equals 0. If you think about it, if you don't have this, so I have kind of like, how can I draw it? So it's a bit difficult to draw that. I mean, so if you don't have this condition, then kind of solution has a spike in the middle where the derivative diverges. Split this. So necessary. Ensure not singular at tau equals 0 x equals 0. Okay, so let me, because these results are important, boxes around them, emphasize them. Okay. So now we are in principle there. We have this formula for the decay rate. That depends on B. That should say so now. Where do I put it? I put it here. B is equal to C of phi, right? So we solve this equation of motion, and then we get B by plugging the Euclidean action. Okay. And now this problem has a very nice interpretation. And the interpretation is if you think of rho as a time, And this is just an analogy that's kind of useful to gain intuition into how the solutions to this equation of motion behave. So if you think of rho as a time variable, then this is a problem. So this is equivalent to a classical particle again. Evolving this time, rotation mass, time rho. And now if you kind of look at if you remember classical mechanics, you remember that this here, this term acts like a dampening force that kind of slows down the particle. So it's a classical particle, it's a bit weird particle, it's a classical particle that is subject to this time-dependent, because it depends on rho, time-dependent dampening force. So if you always time r, subject to rotation mass, time dependent dampening force. What's this term? Here we go. Okay. So, and I should say, and it's moving in a potential that's again reverted. So moving potential minus v of phi. And that's, if you remember, that's the same as we had for the case of quantum. So let me just draw it now. So this problem maps to the following one. So we have particle moving in the inverted potential. Red. And here's phi naught. And now if you look at the boundary conditions, so it has to start. It essentially starts with zero velocity somewhere at time rho equals 0. And then it's supposed to end up at phi naught at infinite time rho. So what you will get is like a path that kind of, let's say, it starts here. And now it rolls down. But it gains less energy than a normal classical particle would, because it's subject to this damping force. So it goes down, and then slows down, and like at rho to infinity, it ends up here. So you start here at zero velocity at rho equals 0, and you end up here at rho to infinity of the solution. You end up at phi naught. So this is just, again, it's just an analogy, but it's kind of a useful analogy to gain some intuition into how these solutions behave. And more than that, so generically, I mean, there's analytical solutions for certain potentials to this problem, and later we will see one. But in general, you have to solve this numerically. And now, kind of, this intuition immediately leads to a very simple algorithm to solve this. And this is a so-called overshoot-undershoot algorithm. So I erase this because I want to keep this, I guess. Or let me fix this because we just move So, an algorithm to solve this problem is the so-called overshoot, undershoot. And the idea is you just pick a random starting point in this potential. So let me write this. So you start with some value at initial terms that is between phi naught. So this is at rho 0, and let me call this value here phi 1. That's kind of so some value between phi naught and phi 1, some starting value. Now you numerically solve this differential equation. Yeah, so you start then with the bound condition that the derivative at 0 vanishes, right? So zero velocity emission. Exactly. So now you solve this differential equation, you evolve it to a large term. So you of course numerically it's a bit difficult to evolve to rho equal infinity, but you just evolve to a sufficiently large rho. And now there are two options. A. So if I start very low here, then it will just not have enough energy to get here, right? So it will just roll down, then oscillate, because it's subject to this damping force, it will just undergo this damped oscillation. That's one option. The other option is that I kind of start too far high up. And so now it's a little bit tricky because of this time dependent damping force, but you can convince yourself that you can always get into a situation where this dampening force becomes sufficiently unimportant that if you start too high up, you kind of have too much kinetic energy and you go to the other side. So again, you don't end up here. So essentially, if you start too low, you end up here. If you start too high, you end up on the other side. Right? So two options: phi is too much kinetic energy and overshoots. And that means it goes to, evolves to values, goes to phi less than phi naught. Right? It overshoots, it goes to this side. Or the other option is phi does not gain enough. Gain enough kinetic energy and undershoots. And that means it always and stays at values phi larger than phi naught. It never reaches phi naught. Okay, and now the third step in the algorithm is if you're in situation A, then you go back to 1 with a smaller phi. I should call this, let me call this phi initial. That's my initial value. So I go back to 1 with a smaller phi initial. Or initial, then I'm less likely to overshoot. Or if it's B, then I should start with a larger. With a larger phi initial. Then I have more kinetic energy and I'm more likely to reach this point. And so now you can essentially perform a binary search. So the idea is you start exactly in the middle. Your initial point is exactly in the middle between phi 0 and phi 1. And then your step size, you halve your step size in each step. And then you very rapidly converge to the right solution. So you rapidly converge to the right solution. It kind of starts here at 0 velocity and then at very large rho, very large time, and ends up here. Yeah, or?
I have a question. This is not related to the algorithm, but so when we were calculating this bound solution, like you had said that we start from x0, we go till the same energy point and come back to x0. But while determining this, now we are starting from some other point. And this
Exactly, but I mean this is really because we changed the coordinates to this new coordinate row, right? So if you think of it as a configuration in 4-dimensional Euclidean space, it's a bit difficult to think about 4-dimensional Euclidean space, but you can think about 3-dimensional space, for example, then it's kind of like a ball, right? So, and like one direction is the time direction, and the other directions are the spatial direction. And like, so outside of this ball, your field is at phi 0, and inside of the ball, it kind of probes regions of, kind of here, right? So meaning that, so let me just draw this. So if you think of, well, let's do it in 2-dimensional. So if you have, this is tau, and this is kind of x, then your O4 symmetric solution is just this ball, right? Where outside here you are at phi 0, and here you are at, you have to solve the problem, right? But you are at phi bar of 0, at the origin at least, and then it kind of interpolates between these two values. And yeah, so from this you see that in particular, so at tau minus infinity, you're at phi 0, and at tau plus infinity, you go back to phi 0. So it's really the same thing, and the fact that now it looks so different if I write it as a function of rho, that's because I changed the coordinates right now. Right? So now this in rho is now like the radial coordinate here of this configuration.
So you didn't actually find the solution, you found the initial value.
Hmm?
You didn't find the solution, you found the initial value.
Sorry, but
you still have to solve the equation, right? You found the initial value such that.
well, okay, so this is what I mean was involved here, right? So again, so I start with some initial value, some randomly picked initial value. It doesn't actually matter which one I pick.
Yes.
Now I solve the differential equation.
Yes.
And so that's what I meant with
Yes.
evolve to a large rho, right? I solve the differential equation with this initial condition, so 0 velocity.
Right.
Okay, and then there are really just these two options, it's either overshoots or undershoots. Well, except if I just randomly luckily pick the right point, right? But if I don't, then it either overshoots or undershoots. Okay, and then I just have to adjust the step size, the initial value, and I rerun this algorithm. And then again, if I do a binary search, so if I kind of
Yes.
half my step size each time, it very rapidly converges. If I have a problem, if I have to calculate advanced action, that's what I do. So.
But the bounce depends on the whole trajectory, right?
Yeah, of course. And the bound solution is really this function, this whole function here, right? So like this whole thing. So
right.
like the phi bar of rho. So starting at rho equals 0, and then going to evolving to large.
So there's no case of a potential where you can solve this?
No, there are cases where you can solve it, exactly. So and I will show you one example later. Okay, so now there are two important limiting cases for this. So let me draw this here. So two important limiting cases. So one possibility is that I just have a potential with a big difference between the two vacuum. So essentially like I drew it here. We have phi, something here, and then it's much deeper here. It's a so now I have to flip the potential. Again, essentially just repeating what I drew up here. Okay, and so yeah, this is essentially this situation. So I start here, I mean, like at some intermediate value, and because I'm subject to this time-dependent damping force, initially the damping force is quite big because I'm at early times. So if I now look at the solution, it will just evolve. I'm plotting the solution. Rho, and I'm starting at this value phi I that now let's assume I found it, this is algorithm, and so initially it will just evolve very slowly, so we'll just go down, but then it will speed up a bit, and then eventually it will go to phi naught. Just goes down, slowly speeds up a bit, and then goes to phi naught. Asymptotically at infinite. And this case is called, for reasons that will become clear in a few minutes, it's called thick wall. So the thick is pretty clear because it's kind of like takes a long time for the profile to change. Why I call it a wall, you will understand in a few minutes. Okay, that was one case. Now, the other limiting case is I have a potential that's very degenerate. And by the way, I'm still at zero temperature here. So these are, you can just think of them as zero temperature potentials that has this feature. Later I will switch on temperature again. And then this could be a situation where you have a phase transition that kind of takes a long time to finish. Whereas this situation, where it's very degenerate, would be a phase transition that happens very close to the critical temperature. So this situation is this. Phi. I have a potential that kind of almost degenerate. So this the difference of energies between the two minima is quite small. Now, flip it. So, this situation, this L is just a little bit higher than this one. Okay, and now if I look for a solution, then so in order to kind of reach this point, I have to be very close to here initially. So the curvature is very small, and now on top of that I have this time-dependent damping force, which means that initially the particle, in my classical analogy, will be stuck here for a long time, until the dampening force becomes sufficiently unimportant, and then it rapidly rolls down to this side and approaches approaches are defined. And if you're not convinced that this is how the solution behaves, then just solve this problem and check it yourself. So, draw this here. So when I draw the solution of rho, then I'm initially stuck. So now it's really very close to phi 1. I can call it phi 1. I'm very close to phi 1, to the second minimum, initially for a long time. And I rapidly roll and approach finite. You can already guess what's the name for this situation. This was sig wall. This, of course, is thin wall. And for this case, there's a nice analytical approximation to this analytical solution, approximate analytical solution to this differential equation. But I will not have time to discuss this. If you're interested, it's everywhere in the literature. So just look it up there. Okay.
Is it guaranteed that you can always find a solution for phi 1 greater, for v of phi 1 greater than phi naught? Because since you have this friction term, it's not obvious that
exactly
almost inherent you can find.
No, but you can always find a solution. So exactly. So this friction term makes the intuition a little bit more complicated, but essentially it works like this. So if you so again, the intuition for why you can find a solution, always find a solution, is that if you have this very degenerate situation, then you just go sufficiently close to this point phi 1 that it stays there for a sufficiently long time that this damping force becomes unimportant, right? And so then that's why it's stuck here for a long time, and then once this damping force is sufficiently unimportant, it rapidly gains energy and goes down. But yeah, I mean, I agree this is maybe not a waterproof argument. So in the end, you just go and solve the problem numerically to see how it works. Okay, let me see how I'm doing this time. Okay, good. So, now, this is still quite abstract. I mean, these are really like the bound solutions that we use in the path integral, but as you will see now, they actually map to something very physical. Let me erase all this. As I already mentioned, well, in the beginning, and maybe also afterwards a few times. So what is the outcome of this decay process? Right? The outcome of this decay process is a region in space where I'm already in the. I erased it again. Sorry. Let me draw it once again. So this is the situation. So a region in space where I'm already in this true vacuum here, in this deeper vacuum, whereas outside the theory is still stuck in this false vacuum. So I have like a bubble, and this is really like the corresponding thing to the bubbles that form during the first order phase transition of boiling water. Right? So I have a bubble, a region where inside I'm already here in this true vacuum, but outside I'm still in the false vacuum. And now the question is how does this bubble look like? So what about quantum mechanics, I go back to quantum mechanics. If I had a tunneling problem. So I had a tunneling problem of some state, some particle localized at x naught. And what happens is that so after the tunneling, the particle appears here on this other side with zero velocity. And then afterwards, essentially, it evolves classically in this potential. So it's really like if it's a wave packet, it just evolves. And now if you remember, the instanton was really this path which led us from this point to this turning point and back. So the outcome of the turning solution now is exactly the midpoint of this instanton solution. So instanton again was going from here to here and back. The outcome of the tunneling process is really just halfway, so just going from here to here. So the midpoint of the instanton. And the same now applies to our quantum field theory problem. So the initial bubble that forms after the phase transition bubble is given by the midpoint of the bounce. And the midpoint is, so let me call the profile of the bubble, let me denote it as phi d. At time, Minkowski time equals 0, and with some spatial dependence, is given by this bounce solution, the solution to this problem that appears in the calculation of the decay rate, evaluated at the midpoint, and I chose coordinates such that the midpoint is at tau equals 0. So if you go back to this picture, this is really like this slice here. So this slice is a function of my spatial coordinates, right? This slice, this is an O4 symmetric bubble, so this slice is like an O3 symmetric bubble. That tells me that is the profile of my field right after tunneling.
So I'm confused. So first you mentioned instant solutions is the same thing as this bounce solution. It's the same.
Yeah, exactly. Instanton, the bounce is an example. It's an example of an instanton. Right?
Okay.
An instanton. Again, instanton it is because it's localized in Euclidean time. Right?
Right. And then the midpoint argument is, so the bubble appears with the mid. So that another.
So the argument is maybe a little bit hand wavy at its stage,
because the initial point is not at the midpoint, right? In the initial point, phi equals 0.
So
phi I is not at the midpoint, right?
So again, the midpoint is the midpoint in time, right? So this is a configuration that.
But we're talking about rho O4 symmetric things.
Exactly. So this is my two-dimensional depiction of an O4 symmetric bubble, right? So the midpoint is this slice here, which is a three-dimensional object. A three-dimensional, well, it's not a sphere exactly, it's an O3 symmetric configuration. That so it's a function, it's a field value as a function of the radial coordinate. It tells me the initial configuration. If I go from the inside of the bubble to the outside of the bubble, how does the field wave change? Because again, the bubble is some kind of solution where again, initially in the inside of the bubble I've already tunneled, so I'm at phi. But I'm not necessarily at phi 1, but I'm somehow in this region. Right? So inside, I'm kind of, let's say, close to phi 1. And then if I go to the outside, I approach phi 1.
So I understand why I'm confused. So you're not confused. So you're talking about the profile of the bubble, let's say, no? The phi.
Exactly.
So it's not actually the bounce solution.
Well, it is, I mean, so the thing is, it's two different things. In the literature, it's actually a little bit confusing how it's kind of, they're usually mixed up, but in principle, these are two different things. So there's a bounce solution, that's really like the path of my field in the path integral, right? Which kind of, so yeah, it evolves in time, so it kind of explores different things in time. And the initial bubble profile is again, it's given by the midpoint. So I don't know how to I'm just repeating. So let me just yeah, let me know how to make it clearer. So
Okay, but the bubble should, in my intuition, the bubble appears like at one point, and then.
no, so the bubble is really like as a full-fledged object that appears.
But in the beginning, so it appears like a.
It appears like this, yeah.
Appear like that.
Exactly. So
But in the water example, it seems that it appears small and then it grows, no?
well, okay, it's a quantum mechanical process here. It's a
Right.
little bit different for that reason. Yeah. So no, I mean it appears like it's really like.
It appears like that, boom.
Yeah, it appears like this. Boom, exactly. So, how does it work?
Okay.
For me, it looks like it has to have that shape because you force your solutions in Euclidean type to be O4, so it must already appear like a sphere.
But it can appear with rho very small. Why?
Kind of okay. So you can think of kind of the growth of the bubble is kind of the initial growth of the bubble to this initial configuration that's given by the midpoint of the bounce. That's kind of the quantum mechanical tunneling process, right? So there is a growth, but you cannot describe it classically, right? So the point is, once the solution is there, it just evolves as a classical field configuration. But this it does, starting from this midpoint of the bounce.
But then what the negative power means in that picture? I don't understand.
Yeah. So I'm going back to that. So okay, let me just so because here I'm still in Euclidean space, right? Here this is a solution of Minkowski space, right? But now they evaluate both at one point in time. So at the moment I don't have to say anything about Euclidean versus Minkowski. But now of course this solution will start evolving in time, right? The question, how does it evolve? So first of all, there's a boundary condition, which is the time derivative of this solution is initially 0. And this is kind of the corresponding thing to what you have in quantum mechanics. So you tunnel here, and then the particle appears here with 0 velocity. This is really the corresponding thing, this boundary condition. The time derivative of the bubble wall at initial times is 0.
So, I have a question, sorry. So when we are saying that it's the midpoint of the bounce, so why can't we just directly calculate like the tunneling from x0 to that midpoint instead of like calculating the bounce?
Because so the whole reason for this formalism was that of course in quantum mechanics you can just solve for the wave equation, right? But we cannot do this in quantum field theory. There's no notion. I'm not even sure you could define this problem like this in quantum field theory. So essentially the reason why we went through this whole complication, derived this relatively scary looking formula, was that you cannot exactly do the same thing in quantum field theory that you did in quantum mechanics. So you have to take this slightly to determine that.
So now So the B that the subscript B that you put in the
So this is really like
this B for bubble, not
this is not a B for bubble. Yeah, sorry.
So that was my confusion.
Okay, so this is my notation. I've not. I mean, so okay, let's make it clearer. So this is bubble.
Yes, this is bubble. So of course the bounce is Euclidean, so
Exactly. So yeah, the bounce is Euclidean. So this is the bounce solution, and again, the statement is that the initial bubble that forms is given by this bounce solution evaluated at tau equals 0. So, right, so and again, just let me repeat it once more. So again, so because if you go back to quantum mechanics, the bounce was kind of this pass from here to here and back, and so kind of the initial state after tunneling would be going from here just to here. Okay, so these are the initial conditions, and afterwards it just evolves as a classical solution, satisfying.
and then Minkowski time, of course.
Of course, now it's all in Minkowski time. So. Bubble. So just satisfying the usual equation for a single field jet. Okay, another point is we've already solved this problem. And we solved it because we solved this problem. The point is that the solution to this problem, so now, again, so this is the initial configuration, the initial value, and now I want to know how this bubble that forms evolves in time. And this is really just the analytic continuation of this solution in Euclidean space back to Minkowski space. So it's very simple. Phi bubble of Tx is equal to bound solution evaluated at. So now just before it was plus tau squared. Now we go back to Minkowski time, so I get minus t squared.
So the O4 symmetry still continues, right?
Yeah, so the O4 symmetry now maps to a O3-1 symmetry.
O3-1.
Yeah, exactly. Exactly. And so yeah, so you can easily, so again, if I kind of, because this is just, if I go to Euclidean space, this is just the equation that we have there. Well, not exactly, but this was the equation that we had before before we went to the coordinate row, and then you can also convince yourselves that kind of these boundary conditions are exactly kind of matching to what we had before. So the solution of the bubble evaluated to later times is really given by this bound solution, and we do continue back to Minkowski space. So let's see what that means. You just draw a picture. So I drew these pictures for the bound solutions before it that we get. So now, I can use the same. I can use this relation to map it to the solution of the bubble profile at a given time. So let's first draw it for times t equals 0. So we have something that looks like this. Configuration that kind
So what is in the x-axis? This time?
Yes, I should say that. I'm now drawing slices at
different times.
At different times, exactly. So this is at time equals 0.
So that's how the profile evolves.
Exactly. So this is kind of the initial profile. This tells you kind of if you go from the inside of the bubble, the field has some value phi I, which is close to phi 1, right? And phi I was determined from solving this problem here, right? Using the Overshoot-Undershoot algorithm, for example. So it has some value phi I inside of the bubble. And then if I go to the outside of the bubble, I can asymptotically approach phi naught, which is the false vacuum, right? So the solution to this problem gives me both the bounce action and also the profile of the initial bubble. Okay, and now I can just evaluate it to later times by using this relation. So now if I just go to later terms, then just everything will be shifted along the x-axis, right? So if I go to later term t1, and then even later time just shifted. So you see that kind of the bubble once it's formed. So it's formed like this as a classical configuration, and now it just evolves classically afterwards, and it just expands. And this answers a question that one of you had, like in the very first lecture, for how this bubble behaves after it was formed. I mean, so it behaves like this. So it just evolves as a classical field configuration and grows in the sense that kind of, so the field will actually kind of classically approach this value inside of the bubble. So what happens is that kind of the bubble grows, and the region in space where I'm in the true vacuum also grows, right? So this is how the phase transition proceeds. So gradually, as a growing bubble, the vacuum is turned into the true vacuum. So now I can, like, let's just define, I now draw, like, so now I can just draw the time dependence of a given point here on this bubble wall profile. So I mean, what people usually call the bubble wall is kind of this transition region, right? So it's kind of I mean, especially if you have like a narrow wall, you can really clearly define it, like it's phi initial inside, goes to phi 1 inside, and then phi naught outside, and then it's kind of...
So does it become thicker as well?
No, I don't think it... I mean,
so
it doesn't change the vacuum. It changes, the profile can change if you now have plasma and the F is a plasma, then the profile change. But in vacuum, it always stays the same. It's
right.
really just...
Because yes,
I mean, the only thing is that, so kind of our solution, yeah, so inside of the bubble later it will just approach this value. Like this part always stays the same. So. Okay, so let me just draw, so if I draw like the time dependence of a given point along this profile, how it evolves in time, right? So let me call this point here xb of t, right? So now I just want to follow how it evolves in time. So this is really just so what I'm really asking is how does this being constant evolve in time, right? So this being constant maps to a given value on the bubble wall profile. So the question is, I really want to know is constant, how does this evolve in time? So change this value c, depends on my choice, so then x is equal to square root of t squared plus c squared, right? So I'm drawing this so this tells you, now the slope of this function tells you kind of the velocity of the bubble wall, right? So the velocity of this point on the bubble wall. It initially starts with zero velocity, but then very rapidly approaches the speed of light. So this is kind of, the slope is 1 here, so the wall velocity approaches 1.
On the figure above, I'm a little bit confused because you always start on the false vacuum, so you should start with phi 1 at all times?
No, we don't start again. So we start. No, I mean, essentially the field configuration doesn't necessarily tunnel to this minimum here, but it goes to some point. That, I mean, this phi I was the one that I determined using the Schwabisch-Granische algorithm. It's kind of that's the initial value of this is phi bar of rho equals 0. That's the initial value.
No. The real vacuum is phi 1, right?
Yeah. So okay. So the point is.
Go to phi 1.
So exactly. So the point is, you initially just go to phi I,
Yeah.
which is close to phi 1,
Yes.
and then kind of at the inside of the bubble, the field evolves to phi 1.
You're right.
Also in the classical way. I mean, this part I didn't describe yet. So, and I've also not. I mean, you can also solve for this evolution,
No, that's right. Okay.
but I mean, usually phi 1 and phi I are
Of
close
course,
to each other,
yeah,
so
yeah.
it's a small difference.
So what I said is wrong. So in the bubble, you have actually close to phi 0, false vacuum.
Exactly. In the bubble, of course, you're close to phi 1, which is a false vacuum, and outside.
Phi 1 is the true vacuum.
And sorry, the true vacuum. Inside of the bubble, you're close to.
Oh, yes. Okay, no, inside of the vacuum should be close to phi.
Exactly. Inside of the bubble, you're close to phi 1, which is the true
Close to
vacuum.
phi 1.
Outside of the bubble, you are in
Outside
the
the
false
vacuum,
vacuum, which is phi
false
0.
So that's why you go to phi 0. Okay.
You took your solution and then you evaluated it, evolved it forward in time.
Yeah.
But if you try to evolve it backward in time, it should be symmetric, right? The bubble would also expand backward in time.
Yeah, but I mean, there's no, that's not physical, so you cannot evolve it backward in time. So, I mean, because backward in time, that's really like this quantum mechanical trunnion process that afterwards evolves classically. But I mean, if you evolve it backward in time, you're doing the wrong thing. So, because you're kind of trying to describe this quantum mechanical trunnion process by some classical evolution. So yeah, it only makes sense like starting from time equals 0 in our choice of coordinate system evaluating to larger terms. Okay, so let me just get a bit. Okay, yeah, good. I have a little bit of time still. Okay, I just wanted to. So remember we discussed, I think in the second lecture, that in the standard model we actually have this situation, right? If the standard model is valid up to the Planck scale, if there's no new particles up to the Planck scale, then our Higgs potential looks like this. So we are here today, but there's a deeper minimum at larger Higgs values, right? And so for those of you who are still worried about the possibility that we may eventually tunnel to this point, Sidney Coleman has some very reassuring words that I wanted to read to you. That's from his energy lectures, he uses some instantons. So he writes, okay, so he has this picture that I will not reproduce now. So he writes that a stationary observer. So the idea is that kind of you are somewhere here, right, and the bubble somewhere forms, right?
And it's coming at you.
And it's coming at you, exactly. So, and now he writes, a stationary observer cannot tell a bubble has formed until he intercepts the future light cone projected from the wall at the time of its formation. Okay. A time r later, and r is kind of the initial size of the bubble. that is to say on the order of 10 to the minus 10 to 10 to the minus 13 seconds, which corresponds to phase transitions taking place at energies between 10 to the minus 14 GeV and 10 to the 6 GeV, so it covers kind of everything. It in particular would cover the case of the Standard Model. Okay, so at time r later, that is to say on the order of 10 to the minus 10 to 10 to the minus 30 seconds later, he is inside the bubble and dead. In the true vacuum, the constants of nature, the masses and couplings of the elementary particles are all different from what they were in the false vacuum, and thus the observer is no longer capable of functioning biologically or even chemically. Now, since even 10 to the minus 10 seconds is considerably less than the response time of a single neuron, there's literally nothing to worry about. If a bubble is coming towards us, we'll never know what hit us.
True.
So I hope you sleep better now. Okay.
So there were worries that when the LHC was turned on, it would...
Exactly, it would trigger that, right? Yeah.
The problem is very flowery, though.
So, okay, so the last thing I want to say is that, as I already mentioned, this ugly guy here we will not evaluate. I'm not sure, maybe there's some potentials in quantum field theory with which you can do it, I'm not sure, but I mean, in general, it's impossible. So what one does is instead one makes an order of magnitude estimate. And one just, I mean, it can depend on a few scales in the problem. So one is because you have these temporal and spatial derivatives. It can depend on the size of the Burns configuration, or which is really just the size of the initial bubble that forms. And if you match the dimensionality, it must depend to the fourth power element. So size of initial bubble. It could also depend on the starting value of the field. This phi I here, the initial value. And another parameter could depend on this. And the second derivative of the potential evaluated on the Burns power. So for this you have to find some kind of average. And typically all these quantities are roughly of the same order of magnitude, and what people usually do, they just say it's set it equal to this. And I mean, there's this error, I mean, the point is again that kind of because this really, the important part is like this exponential dependency, right? So the prefactor here doesn't affect things too much.
What sets the scale for the initial radius of the bubble?
So it's usually,
V dot should be V.
yeah, it's usually kind of, I mean,
Second derivative should be. That's the
that's
only
D, I guess, yeah. I mean, in the end, there's usually one scale, right, which is kind of the size of the vacuum you're tunnel to, right? So it's kind of so essentially find out, I think, will in the end set the scale of all these parameters. I mean, it could be different, depends a little bit on your potential, but in general, it would be roughly of the order of phi 1, so of the position of the fault. Okay, so let me hurry a bit. So far everything was at T equals 0. Now let's switch back on temperature. Now, let's switch back to temperature. Okay, we have already learned what to do. So, okay, one thing is that we now have to use the thermally corrected potential. We will have to calculate this potential that the corresponding quantum field theory is described by quantum field theory in Euclidean space, where the Euclidean time direction is a circle of size beta, or the inverse temperature. So, because we are imposing periodic boundary conditions, this is a circle of size. So in deriving this formula, we went to Euclidean space already. So now to switch on temperature, all we have to do is to make the time direction finite. And so I drew this picture, so let me draw this again. So if you look at the Vance configurations, let's consider this compactified time direction. So tau, and the size is going from 0 to beta, right? And let's first make the temperature very large, meaning that beta, which is the inverse temperature, becomes very big. So this is kind of very big, right? So in this situation, at low temperature, nothing changes compared to our calculation. So we can think of like these instantons now, and these kind of four symmetric configurations. Because you can have several of them, they pop out, they suddenly appear, right? They disappear again, and then nothing happens, and they appear, disappear again, and so on and so forth, right? So if the temperature is low enough, if beta is essentially a lot bigger than the size of these instantons in Euclidean space, the whole calculation goes through. But now let me make the temperature bigger. So now raise T. So then this becomes smaller. So now they start to be squeezed together. You know, it's a situation where they kind of start to overlap. And now if I go to an even more extreme situation, where it's even more, eventually they will just be smeared out in the extra dimension. And essentially I just have kind of like a constant configuration of the Euclidean time. So what this tells you is that kind of if you switch on temperature and you go to high temperature, then your O4 symmetric bubbles, which I drew as circles here, right? In the limit gains of very high temperature become those three symmetric bubbles. And so now there's a few small changes that you have to do in this case, but I mean most of the formalism just goes through like before.
Can you repeat why you have this effect that when you increase the temperature, the bubbles get closer to each other?
Well, I mean, essentially saying that it's kind of. So the bubbles really have a size in Euclidean space, right? I mean, it's not bubbles now; these are really instantons, this is really like four-dimensional space that I'm depicting as on a two-dimensional plane now, yeah, and so they have a certain size along the time direction, right? So now as the time direction becomes smaller and smaller, you can also just draw one bubble and And you see that if you make it small enough, and one instanton, if you make it small enough, it doesn't fit inside anymore. It's a yeah. So that's why, like, if you take this limit of very large temperatures, eventually, like, the symmetry of the instantons will change from O4 to O3. Right? So that's.
And also the dilute gas instanton. So the dilute instant approximation breaks.
But then it doesn't really, exactly, so then it doesn't really, yeah. So I think you can think of this, so you've derived this in the dilute gas approximation, and now you just take this limiting, this limit, I mean, I guess you can probably do some cross checks that this is kind of the right thing to do, but the way I think about it is just, yeah, so this is kind of the situation we derived our formula in, which works, and now we just take the limiting case where the temperature raises and the instantons don't fit into this compact time direction anymore, and so as we get out. Okay. So then what we get is then four symmetric bubbles, four symmetric instantons really. Map high temperature to three symmetric instantons. This was first discussed by Linde in this paper. Okay, and now, yeah, not much changes, so the Euclidean action is sorry. So essentially your incident configurations are now constant in this Euclidean time, right? Euclidean time is finite, so what you get is really just like an overall factor of beta, which is the inverse temperature. So you get a factor of 1 over t, so your configurations are now, let's call this bounce profile now. Just do not depend on the time direction. Get a factor 1 over t from this time integral, and then d squared x, everything else. Let me call this here, for convenience, S3. So this is just this three-dimensional integral. It's a Euclidean action, but just evaluated for this three-dimensional.
So what happens to the derivative?
So again, this just becomes constant in tau, right? So this term goes away. Exactly. So actually I should calculate it. So this goes away, so it just. Okay, then the Euclidean the equation of motion for this profile is again the time derivative goes away, so it's just a spatial derivative and an equation of motion. This. Okay, the last thing is that now, so they also O3 symmetric, so I can write phi as phi r of x. It's really just because O3 is symmetric, I can again introduce the coordinate rho, where rho is now just the absolute value of x. Okay, so then if you plug this in here, evaluate this, you find that you get the same equation of motion. Instead, the only difference is that you get a factor of 2 here instead of a factor of 3. So let me call this let me generalize this. So now Ci is equal to 3 for 4 symmetric instantons, and it's 2 for those 3 symmetric instantons. And the bubble action is given by the Euclidean action of the bound solution for 4 symmetric instantons, and given by this S3 divided by the temperature for those 3 symmetric instantons. So now, I mean, what people just do in general is to evaluate, so to solve this problem for both cases, for the O4 symmetric case, for the O3 symmetric case, calculate this coefficient B in both cases, and then just take the smaller one, because these are kind of the configurations that will dominate. And typically you find that at high temperatures, the O3 symmetric dominate, and at low temperatures, the O4 symmetric dominate. It depends a little bit on the problem at hand, if that's true or not. Okay, so yeah, yeah, just to summarize what we did. So now we essentially we learned 3 things. We learned how to calculate radiative correction to a scalar potential at 0 temperature. We learned how to calculate radiative corrections, thermal radiative corrections, and the last thing we learned is how to calculate now the potential, the decay rate from between 2 vacua. And now we are essentially ready to describe phase transitions. Unfortunately, now time has run out, so I will do that next time, and then start also hopefully talking about gravitational wave systems.
Thank you. More questions for Benedict? Okay, great. So see you guys on Friday for the next lecture for get the phase transition.
Exactly. So then we will relax a little bit and tunnel.
Acho que hoje vai estar melhor. Acho que a aula passada fui eu que coloquei para gravar.
Vai dar para mudar?
Hoje mudou, mas a aula passada não já foi gravada. So I cannot join for lunch. Student has a meeting also till 1.
Okay, so I'm fine to go.
Okay, so so the student will probably go up, or you go to the student's office.
Yeah.
Okay.
I go to the office.
Okay, very good.
Okay.
Atrasado, não sei se vai ser importante para pegar algum certificado depois ou
Se você quiser,
eu acho que nós terminamos passado, mas eu atrasado.